Suppose I have a rather large positive charge, and I bring it towards something metallic. What do you think would happen? Well, one sort of experiment you may have done in the past is taking a comb and, after rubbing it through your hair, put it next to some running water and you'll notice how it'll be deflected. And you're told that's supposed to have something to do with the fact that water is a polar molecule, it has electric charge, and it aligns itself in such a way as to be attracted to that charge. And we can talk about that now in terms of charges and electric fields here. And if particularly we want to look at something that we are going to call a conductor, we have to imagine what might be happening. So if we have a conductor and we say it's neutrally charged, it doesn't have any charge on it initially, in the presence of some other charge, we can imagine that the electrons are basically free to move around. So in that case, that we can imagine that any of the positive charges would actually be repulsed by this object, while the negative charges would be attracted. So we can imagine a bunch of little negative charges moving to one side of the sheet, and positive charges would then end up concentrating on the opposite side, as far away from the charged object over there. And it would still be the case that our conductor here would actually still have the same net charge on it. It's just that now the charges have kind of separated themselves out. And we'd expect this to become more and more severe depending on if we can make the charge off to the side here more and more powerful. So this is a key point when it comes to conductors. With insulators, this doesn't take place, and you can't actually get this sort of change in the charge strength on one side of the object versus the other, unless you actually physically contact it and then start moving charges to that. And of course, with a setup like this, you would expect now this object to be attracted. The side over here is closer to the charge, and so the force between these two is stronger than on the opposite side here, and so we'd expect these two objects to then start moving together. In the same way, like I say, if you take your comb, you charge it up, and then put it by water, the molecules of the water will line up in a somewhat similar fashion, and then the water is then a little bit attracted to the comb, and it deflects it from just falling straight down. Now, there's a few things that this is going to imply about what will happen, and specifically, though, if we're dealing with conductors. Suppose now we have some positive charge, and we now want to surround it inside of some sort of hollow shell. So it's inside of a hollow sphere, and it'll be of some conducting material. And let's also say that that outer shell is also charged. And just to give things some numbers, let's say that the inner charge here has a value of positive 10 electric unit charges. And let's also say the outer shell itself has a total charge of plus 25 electric units of charge. Now let's ask, if I was to look at the surfaces of these materials, what would I expect to be on those surfaces charge-wise? Since we do have a charge in the center, we could expect that actually the charges in the material to move around, and the negative charges would be attracted towards the center, and the positive would then be moving out because of that mutual repulsion. Question, though, might be how much? Well, one thing you might expect is that the charges that would go out to the inside would be the same strength, the same magnitude as that charge on the inside. And on the outside then we'd have all these sorts of positive charges. Something like so. And if the charges on the inside surface here weren't equal to the charge amount here, let's suppose that if the charges that moved here had a value of, say, 5 electric units of charge. Well, in that case, you'd actually expect then that the force between these two to be actually stronger than between these two here. So in that case, there'd be even more negative charge that would actually try to move here to try to balance this out until the strength of attraction here was equal to the strength of attraction between here. And also the same sort of thing, if there was more electric charge there that was greater than a value of 10 in magnitude, then the attraction between here would be greater, and then it would balance out. So we'd actually expect then the inner surface to work out to be negative 10 electric units of charge. What about on the outside? Remember, for the entire shell, it needs to have a charge of positive 25 electric units. So if the inside is at negative 10, then the outside, to balance that out, is going to have to be positive 35 electric units of charge. Now, one might also then consider the question of, what about the electric field strength going through all of here? You have charges on the inside, you have charges on the surfaces. This might be a little bit difficult to first think about, but it actually simplifies if you actually try using this with Gauss's law. So suppose we have a few different radii to work with. We could say the inner shell there, that inner charge has a radius of A, the inside radius of the surrounding shell has radius B, and then to the outside we have C as that radius. Let's give ourselves some room to play around with then. So there's basically a few different regions that we can try looking at the electric field. We could look at the electric field between radiuses A and B, so the inside of the shell and outside of that central charge. We can look at the radius between B and C, basically inside that conducting shell outside, and we can look at the radius outside of C. So, as we remember that Gauss's law is defined as saying the flux through some surface is equal to the surface integral of electric field dot dA, A ultimately being about the surface integral, the surface of the Gaussian surface we're going to put into here, and equal to the charge enclosed divided by epsilon naught. So if we wanted to say look at the electric flux from outside of this entire setup, it's going to be fairly easy. So first off, what sort of surface are we going to use? Well, to me, I look at this and I definitely see spherical symmetry. So I probably want to use a sphere for my Gaussian surface. In which case then, my integral is just going to be E dot dA equals the charge inside epsilon naught. And the charge inside is just the total charge I had here. The outer shell has a charge of plus 25. The inner shell has the inner point has a charge of 10. So I know the charge inside is going to be total of 35. Nice and easy. Okay. And the area in this case is the surface area of a sphere, which is 4 pi r squared. And so with that, let's give ourselves a little bit of space, and we see now that the electric field is just going to be Q enclosed epsilon naught divided by the area, and that will give us then plus 35 electric units 4 pi r squared epsilon naught. And remember, this is specifically for r greater than C. If we want to look inside, then we're going to have to do a different integral, a slightly different integral. So we'll put this out of the way for now. And let's look at the space between the point charge and that outer sphere. Well, really we can just set up the same integral that we've already had here, but the charge that would be inside a Gaussian surface would only contain the central point charge, in which case that electric field is simply plus 10 electron or electric charge units, 4 pi r squared epsilon naught. So very similar as before. But again, remember this is just between that point charge and the inside radius of that sphere that we've drawn, of that conducting shell of a sphere. So that leaves us then with the radius that is actually inside that conducting sphere that we drew. So if we again do the same sort of symmetry with this entire setup, if we just try to have a shell for our Gaussian surface that is inside of that, well, how much charge is inside of a shell that's basically within radiuses b and c? Well, remember that on the inside surface, we have 10 units of electric charge, negative, and that charge in the center is positive 10, which actually means there is no electric charge inside, no net electric charge inside a sphere that we draw that would be between radiuses b and c. Well, that means then for a radius between b and c, the electric field is 0. We can actually then extend this if we use some other techniques to actually show that inside any conductor there is no electric field. That should be an interesting result. It also tells us then that actually all of the charge will be on the outside surfaces of any sort of conductor. Only way to not have that be the case is you have an insulator where the charges have great difficulty moving around. In this example previously we had these nice symmetries to work with to use Gauss's law to show that sort of situation. But this is also going to work with any sort of arbitrary shape. So I could even have an object that looks a little bit weird like this, and if it's a conductor and I charge it, then I'm going to see a bunch of electric charges on the surface. So let's say I've charged it positively all over the place. If it is a conductor, those charges are going to be nicely distributed. In fact, it's going to be uniformly distributed. Why would it have to be that way? Well, if there's any point on the surfaces here that were more densely charged than some other point, then the mutual repulsion of these guys is actually going to force the rest of the charges around until they finally even out. So in fact, it's all going to be about the same density of positive charges, in this case all the way around. So if I want to look at some random point, let's just say, I don't know, right about here, let's call that point 1, and some other point over here, point 2. They're going to have the same charge density at those points. And since they have that same charge density, they're going to have the same electric field, they're going to have the same electric potential at those points. There's going to actually be no potential difference across the surface. So delta V, the electric potential will be 0. Again, because from what we know from the definition of electric potential for a charge, and the same charges in both places, therefore the potential has to be the same. Another way to think about that is if you think of the electric field lines all going straight out from the surface initially, and if you're doing some sort of a path integral, as you would if you were, for example, trying to do the integral of E dot ds, well, in that case, if you're going along the surface here, then at all points when you're going along the surface, that is going to be perpendicular to your electric field line. The electric field lines are going perpendicular outward away from the surface, and you're going along the surface parallel. So those are perpendicular, and so the dot product here is necessarily 0. So in case I'm taking the integral of a whole bunch of zeros, gives us nothing then. And of course remember that negative integral E dot ds is simply change in potential. As we said, that is now 0. So that's actually two ways to try to think about why along the surface then there is no potential change. what about on the inside if you had some sort of, say, a hollow cavity? So let's draw something a little bit different, but again, it can be any shape we want. So we could have something like this, and there's some sort of internal hollow cavity here. Well, again, whatever charge is going to be on the inside surface, it's going to evenly distribute itself. Again, we can say it's a bunch of positive charges. So now if we wanted to look across this cavity then, let's look at some point 1 and point 2 here again. Well, again, at those 2 points, it's going to have to be the same charge density for the same sort of reasons we said before. And even if we had our line integral going not along the surface, but directly across in any path we just so decided, well, again, we know that the potential of those 2 points are going to be the same. It's the same electric charge at those spots. So, once again, we then know that the change in potential is 0. It's the same potential at both spots. And because this time I've actually taken my integral line, my path length actually not along the surface, and then thus perpendicular to any electric field line, but with any path I might take. This will be true for any path. So for any integral I do, it's going to be the case that for any E dot ds, this is going to have to be 0. Well, the only way this is going to be true, the only way that every possible path I might take from point 1 to point 2 to give me no change in potential, and so for this dot product to always be 0, the only way that's going to work is if the electric field inside the cavity is 0. So this is actually another proof then of why you're actually safe inside of your car or inside of a Faraday cage, inside of a conducting Gaussian surface, that no matter how charged it gets on the outside, so long as you're not touching anything, the charge can't get to you. There is no electric field inside. And then similarly also is going to be the case if you happen to be inside the conducting material itself. Again, all those charges are going to be on the surfaces, and you're also going to be safe. Now, putting yourself, say, in molten copper to protect you from electricity, from lightning bolts and such won't be effective, but inside of a cavity, much more plausible to be safe. Because now from this, we can see clearly that there's always going to be 0 potential inside a conductor. Now, I've continuously said this is for a conductor. This is not true for an insulator. Why is that? Well, with an insulator, you don't have this free movement of charges, so you could potentially have a big, strong concentration of positive charges here and either less positive charges here or even negative charges there. They're not free to move, so that won't be the case, and so that line integral I could do from, say, here to here won't necessarily be 0. And so in that case, I can have an electric field in there. And of course, as you can imagine with a conductor, any field that any of these positive charges are going to have are just going to cancel each other out because they're completely surrounding you. If you have an insulator, you can have charge differences, and then you're going to be in much bigger trouble. Now let's use this information as something purely practical. Suppose you're a friendly neighborhood Spider-Man or Spider-Woman, and you're dealing with Electro. Never mind how Electro actually has such huge charges, but if you want to protect yourself from being very badly burned by the villain from the recent Spider-Man movie, what could you do? Now, if you've seen the film, one of the bystanders claims that Spider-Man is able to protect himself so well because of the rubber or neoprene suit he is wearing. Of course, you'll guess that the suit he's wearing isn't very thick in rubber, and of course it's probably somewhat porous, so that way he's not sweating to death. And that is not a very good sort of protection from the sort of voltage being portrayed in the movie. I mean, after all, he is firing lightning bolts, he is using steady electricity. And even a rather thick pair of rubber gloves, a small hole in there, and you are going to get fried. Spider-Man is not going to do himself well just by standing on the ground or on a building and hoping the bit of rubber covering his body is going to protect himself. So the key thing, though, is that rubber is supposed to be an insulator. So you have some sort of material, and even if some sort of charge is built up on the outside, it won't necessarily get to the other side because it has such difficulty moving through the material. But again, because Spider-Man's suit ultimately has to be somewhat porous, so that way he isn't drowning in his own sweat, means that it's going to be very easy for his skin to make contact with the neoprene surface and the charge then move to his body and then big time zap. Same sort of thing then happening if you have thick rubber gloves and you have a small hole and then you touch an electric wire. Very bad stuff. So this is not going to be a good solution for him. The other solution given, that somehow charging his web dispensers will somehow protect him because of magnetic properties, is just showing that the people who wrote the script didn't really understand electromagnetism that well. But there's a much simpler thing we could do if we use the concept of conductors instead. Now, of course, having Spider-Man just holding a metal rod would be bad because now you would expect him to greatly attract any lightning bolt sent by Electro. But suppose instead of being Spider-Man, he were the Iron Spider. So if we really start mixing together Marvel characters. Well, in that case, his entire outer surface is going to be a conductor. So to kind of draw that, we would have a conducting shell and inside a friendly neighborhood Spider-Man. So no matter how much electric charge Electro would shoot at Spider-Man, all that electric charge would be on the outer surface of the armor that Spider-Man would be wearing in this case. So with that, it means inside there would be no electric field from the previous things we had shown before. And so if there's no electric field inside and it's completely independent for how much Electro is shooting at him, in that case, Electro's entire weaponry is absolutely useless against Spider-Man, if he is in Iron Spider-Man form. Now, of course, if we're going to be following the comic books, we know that Peter Parker does not have a huge amount of money. He cannot afford his own Iron Man suit, and he's not part of the Avengers, at least not yet, and because of copyright issues, probably won't happen in the films anytime soon. But if he got himself, some decent tinfoil, or if he could even, rent, a set of medieval armor or something, bam, Electro can do absolutely nothing against him, no matter how charged up he happens to be. So, if you find yourself in the situation of having to fight off electric supervillains, get yourself some medieval armor, and you'll be carrying the day.